I would like to introduce our vice chair and speaker for the evening. Dr. Michael Seeman is the president and founder of ETA-ONE-POWER, an engineering software startup company. ETA-ONE-POWER is the company behind DeDesigner, the first simulation and analysis software that focuses on increasing power density and efficiency of power supplies. Mike received his SFBAC degree from the Massachusetts Institute of Technology and his MS and Ph.D. degrees from UC Berkeley. He's a member of the IEEE and vice chair for the SF Bay Area chapter of PELS. We learn something new every night. That's great. All right, please join me in welcoming Mike.
Thanks for the introduction. So I'll be talking about the optimization of power supplies and their magnetics. So first of all, I'll start with a quick outline. We're going to be talking about power supply design optimization, which means I should really tell you what I mean by power supply design optimization. We'll look at system requirements placed on magnetic structures in terms of external requirements on the design of them. And in order to optimize a transformer or an inductor in this context, you really have to understand the losses in order to get the smallest size, the most efficient inductor, and most importantly, something that's reliable and will act how you expect it to act. We'll then look at magnetic scaling, look at if you increase power levels, how much larger the magnetic gets. If you increase frequency, does the magnetic get smaller, and by how much? We'll then look at software tools for whole converter analysis and optimization, including a few case studies, and then finally wrap it up with some conclusions. Let me start by talking about some common figures of merit for power converters. Number one figure of merit for almost every power converter out there is cost. For any two power supplies that meet the requirements, the cheaper one will always win. The next figure of merit is power density. You want your supplies smaller and smaller because they have a very utilitarian function. And if you have a fixed size box or a server or something like that, you want to have most of the space, as much space for computation or storage or something interesting for the customer, not a power supply. The next few things are important. So reliability, so your power supply doesn't break. Time to market, the faster you put it out there, you beat your customers, and you reduce your development time. Supply chain reliability, making sure you can obtain every single part in your power supply. Passing EMC, UL, all those checklist things you do at the last minute to get your power supply out, those are all required. And then when you get down to things that engineers care about, like efficiency and transient response, those are typically specifications. And at the end of the day, they only are means to the overall end of having a working power supply. And these constraints are really fall into three different categories. Technology-based ones, such as efficiency, transient response, and power density, are what engineers care about. And that's what you have to consider while designing your power supply. But then you go into the specifications, meeting all the specs in terms of efficiency or size or all these reliability. And then manufacturing, making sure all the components are available from multiple sources if possible, as cheaply as possible. So anyway, let's dive into the technology, because that's what we're all here for. We're all technologists. And then now let's look at how we achieve the number two goal here, power density, from a technology standpoint. So for a power converter, there's a trade-off between efficiency and power density. So typically, as you make your supply more and more dense, your efficiency drops. Or to make your power supply more efficient, you have to make the components larger and your power density drops. So there's a trade-off here, and that trade-off usually involves switching frequency. So the faster you switch, maybe you're less efficient, but your supply can be made smaller. There's also a thermal limit. So the smaller you make your system, the less heat it can dissipate just because of surface area. So that yields a curve like this. And your optimal design point is going to be at the intersection of these two curves. The smallest possible solution that's reasonably efficient, but that meets your thermal constraints. So if you can move from this base technology, and in terms of a technology here, I'm saying topology or device selection options, so magnetics or semiconductor devices. If you move to a new technology like using GaN or silicon carbide or some fancy new topology that has EVS and all that stuff, or maybe a new magnetic material, we can shift the curve up and to the right. This means we can get either higher efficiency or higher power density. But again, to meet that optimal point, you have to stay along that thermal constraint line. So that means you're going to be increasing both power density and efficiency. And finding that sweet spot is often takes a lot of work. And that's really what ETA-ONE-POWER and the software I'll be talking about, ETA-Designer, is trying to do. So how do we do this supply optimization? There's a lot of things that come into it. We start with the topology. We need to simulate that topology to understand what the waveforms are, what the currents and voltages are, and how to control it to make it stable. So we use a software package, LT-Spice maybe, or a Simplis, something like that. Then we need to pick parts. And to go pick parts, you go to DigiKey, or maybe your manufacturers come and visit you and say, this part's much better than our competitors, and maybe you trust them or not. But anyway, you want to find a cheap part that works the best in your supply. Then you want to calculate how efficient your supply is, so you're going to go through a bunch of math using textbook models or other things you've seen in papers and so forth. And you wrap it all together in Excel, in a spreadsheet. And every designer has a spreadsheet that tries to estimate the loss of their power supply. And it does it to varying degrees of accuracy. And if you're fancy, maybe you come up with a MATLAB script to optimize this, or something like that. What ETA-Designer does is a bunch of things. So it's trying to wrap all these into one product, into one piece of software. So we start with a flexible schematic editor, so you can create whatever topology you want. I mean, you can start with a buck. We can actually automatically design a buck for you with input and output voltages. But you could also design a custom LLC converter or full bridge LLC or whatever you come up with. You can draw it and you can simulate it. And not only can you simulate it, you can simulate it basically instantly. So we came up with a really fast simulator. Basically, when I was running simulations, they took a long time. And by the time you got back to it, you forgot what you tweaked. And you can't really do optimization with such a long iteration time. So the purpose of this software is to iterate very quickly. So we have a fast simulation engine. We've developed a controller design such that you can come up with a control for the topology. You can come up with a switching waveform, either straightforward PWM or something very complicated with a variable frequency with ZVS or CCS, zero voltage switching, zero current switching, sensing, current mode control, all that stuff very easily. I won't be going into too much of this, but just to give you a background of what the basis is. Component database is a large set of components in the software, but you want to know how they act or which part's the best for your position or for a certain spot in the power converter. So you can bring up a list, and before you even choose one, it substitutes each of those into the converter, tells you how efficient it's going to be, tell how much, you can see how much heat it dissipates, and it tells you how much it costs. So it goes off to Octopart and figures out, can you buy it, where can you buy it from, how much it costs. So you can, before you design it in, you can know if it's available. Magnetics optimization, that's the topic for tonight. But we can simulate custom magnetics. You can design your own core shape, or put in your own core shape, put in your own windings, slits, wire, etc. I'll get into this in a lot more detail and find all the losses associated with that in the context of that power converter, not idealized waveforms, but that power converter. And finally, efficiency modeling. You can't close the loop without understanding efficiency. So we have real-time calculation of efficiency in both loss breakdown. You can figure out the majority or the components that dissipate the most power. You can also sweep the efficiency over variables such as input voltage, output current, maybe some other variables as well if you go in and define those. Okay, so let's go back into magnetics. That's the topic for tonight, right? So magnetics has a bunch of requirements placed on it. So we have some circuit requirements from the topology, so including the winding configuration, like the number of secondaries you have, whether they're center tapped or not, if you have an auxiliary windings, the turns ratio between these different windings, the frequency of operation, the volt-second product applied to the transformer, to calculate saturation, and the peak currents through all the windings. You also have another set of requirements, so cost, obviously number one, but how big it is, the volume, how much space on the board it takes up, how much height it takes up, whether it fits in your box. The mass, sometimes mass matters, especially if it's going in something that flies. Safety isolation from do you need reinforced isolation between primary and secondary? How much voltage does it need to withstand? That sort of thing. And then temperature requirements. Is it in a high temperature environment? And how hot can it get with regards to ambient? So all these requirements come together to define a bunch of decisions you have to make about the transformer itself, like core size, shape, core material, turns count, wire size and type, winding procedure, and the means of achieving the isolation requirements you have. So taking those requirements, you want to design the most efficient, the smallest power supply that meets, or magnetics, transformer, inductor that meets your requirements. So that requires understanding where all these losses come from. And that's what we'll be spending a fair amount of time on. That's the most interesting part about magnetics. And it's pretty difficult to calculate, but that's part of what I incorporated into ETA-Designer, so you can calculate these very easily and do iterations in a matter of seconds. Okay, so we'll start by looking at DC loss. This is the most straightforward to calculate. It's I squared R based on the copper that you wind in the coil. There's some more stuff to talk about here about how to minimize that resistance. Next step is core loss. So this incorporates the hysteresis loss as well as the eddy current loss in your core material. And often goes by the Steinmetz equation, which is a somewhat idealized case. I'll talk about that in a little bit. And there's also nonlinear effects that are much more difficult to calculate based on waveform shape, core geometry, DC bias in terms of the current. Then we look into higher frequency or AC winding losses. So everyone knows about skin depth. At high frequencies, the current is only carried by the outer side or outer skin, essentially, of the wires. But there's also a proximity effect and core fringing field effect that can be much more dominant, which are caused by similar mechanisms, but involve a little bit more math. And finally, there's winding capacitance loss. If you look at an inductor, you actually have many wires or many turns, and there's capacitances between each one, and that creates interesting dynamic effects. I'll talk about that too. Okay, so DC resistance, Ohm's law, pretty simple. But when you get down to it, it depends on how many turns you have, the average turn length, what's the diameter of your bobbin, and the cross-section area of copper you can actually put in your inductor design. So things to consider. Planar designs, PCB-based inductors are very common these days, are very popular. But the thing you have to consider is because it's so short, you have a very small window. And not only do you have a small window, if you put a PCB in there, most of that PCB is actually fiberglass and not copper. So you get very little copper. So your DC resistance can be much higher. Of course, you get some other advantages when we get into AC losses, but your DC losses put you at a behind initially, at least. Finally, when you're looking at isolation, to achieve that voltage requirement between primary and secondary, you have to put them far apart. That's either using like tape or using wire with thick insulation. So those are things you have to consider for DC resistance. Core loss. So this is properties of the core itself and power dissipated by the core. Incorporates a hysteresis or hysteretic based on your BH curve, as well as eddy current losses. And goes by the Steinmetz equation, which means that the power dissipated is proportional to the frequency to some power. Maybe it's 1, maybe it's 1.2. It's some coefficient based on the material. And it actually varies with frequency too, so it's fairly complex to model correctly. Times the peak flux density to some other power. And that flux density can be found by either a volt-second product or inductance. Yes? That's the magnitude. So if you have, for example, a sinusoid of flux ripple at some DC bias, it's just the amplitude of that sinusoid. But the most common thing to do here is to look at the manufacturer's curve data. It's a plot that looks like this, and you can find your peak flux density, you can find your frequency, and you can find your power density from that. So, and these capture all the nonlinear effects, some of the nonlinear effects. There's also other factors as well. Okay, so core loss versus frequency. Everyone expects as you go higher in frequency, your magnetics get smaller. That's like a rule of thumb, but it's taken to an extent that's maybe not necessarily realistic. So you see here that the left is a figure of merit, or a performance metric for a core material. And you have a scale frequency on the horizontal axis. So you see that, okay, the figure of merit's going up, and it looks it's going up pretty steeply, right, with frequency. Well, maybe not. It's actually a log linear plot. So if you look at it carefully, over the first decade from 10 kilohertz to 100 kilohertz, it goes up by a factor of 9. So that's pretty good. You get a much smaller inductor at 100 kilohertz than you do at 10. Up to a megahertz, now you only get a 3x improvement over that decade. It's something. But from 1 to 10 megahertz, you only see a 1.7x improvement. So as you go higher and higher in frequency, your core loss doesn't necessarily improve dramatically. You also get a lot more problems that we'll see in terms of AC losses that actually hurt significantly more, especially with transformers as you go up in frequency. Then non-sinusoidal waveforms. Most converters don't use sinusoidal waveforms, and with a non-sinusoidal waveform, whether it's a square wave or a triangle wave, you get additional losses. And there's a number of ways of calculating that. I'm actually not going to talk about it too much here. But basically, you can use a method called IGSE, developed by Dr. Sullivan at Dartmouth. And that actually accurately predicts the core loss based on a non-sinusoidal waveform from a real power converter. And that's what our software uses. So AC winding losses. These are difficult to calculate them, so it's also fairly difficult to understand. And that means a lot of people neglect it and get bitten by it when they build a power supply and test it and see their magnetics getting way too hot. So there's three main factors of this. There's skin depth, proximity effect, and fringe field effect. And all of these have to do with generated H fields or magnetic fields that cause eddy currents in the windings. So the skin depth is fairly simple. It's taking one wire in isolation, and current generated in that wire causes H field, which in turn causes eddy currents to cancel out the currents on the inside of the wire, forcing all the current to flow on the outside. That means you get additional RMS current, additional magnitude of, and that will actually add to additional loss. But the proximity and fringe field effects are important too, because those consider external H fields. So proximity are H fields generated by windings or turns from either the same winding or adjacent windings. And fringe field effect is H field due to the gap emanating from the gap in the core if you put wires close to that gap. So let's quickly talk about skin depth. It goes with the skin depth decreases with the square root of frequency. So as that increases, as frequency increases, skin depth goes down. It's fairly straightforward to calculate, and it's fairly straightforward to mitigate using Litz wire, which comprises of many small strands that are braided in order to equally distribute currents between the strands. Proximity effect. Sorry, this is a bit of an eye chart here, but it's the same effect. So eddy currents are generated in the conductors to cancel the currents on the inside. But that means that externally generated H fields, which basically build up in a stacked winding like this, will contribute much higher losses, much higher currents than you would anticipate. And for a 1D stack of foils like you would see here, which is an idealized case, there's Dowell's equation which you can use to calculate it. But in general, in a 2D or 3D actual magnetic, you need to use a field simulator, like an FEA or something like that, to calculate the losses. And you can use something like a squared field derivative, also again, Dr. Sullivan's work. to estimate these losses, and that's what ETA-Designer does. It uses a 2D field simulator approach. But anyway, if you look at the chart here, if you compare it with what we had before, where here we start seeing effects at 1 or maybe 3, 4, 5 times the skin depth, here we start seeing effects well below 1 times the skin depth. So this proximity effect for many transformers can be dominant over the skin effect. Something to consider. Here's an example. This is a transformer stackup. We have 2 primaries on the outside and 4 secondaries on the inside. So the MMF, or the integral of the amp turns, steps up in 2 steps over those 2 primaries and then goes down. But this is at the low frequency. At high frequency, you see the MMF go to 0 at the inside of each winding layer. And since F is the integral of the H field, we actually see large spikes at the start of and end of each layer. So these are basically currents that are flowing in the skin. And you can see, let's see if this laser pointer working.
Why wouldn't those spikes be rectangles?
So they're not triangulars either. They're exponential decays. So in terms of my PowerPoint skills, triangles are as close as it's going to be. So on the you have the most current on the outside, then goes to 0, and then on the inner side of that winding, you have another spike because of the skin effect again. What you see in this example is that the current flows are in opposite direction. So maybe that winding is carrying 1 amp, but the outer side of that winding is carrying -2 amps, and the inner one's carrying 3 amps. So you can imagine that loss is way higher than you would initially expect. And that's actually what we see in simulation is we get AC to DC resistance or power loss ratio of 4.77. So you're burning more than 5 times the winding power than you would have calculated with just a DC resistance alone. And that would really bite you in the butt. You can actually fix this. So we can go over here, and now we just interleave the windings. So we have a secondary, primary, secondary, secondary, primary, secondary. You can see that our field here is much lower. Again, we have a stair step because of our AC contributions. But it's much smaller, and our currents here are way smaller. And we don't have any reversing currents or currents that are flowing the wrong direction. And here our AC to DC ratio is only 0.65, so we get a significant improvement. So that's something to consider. Of course, this makes your capacitances, which we'll get into in a second, much worse. So I'll talk about fringe field effect a little bit. So as you know, a lot of people use gapped cores for inductors, flyback transformers, LLC transformers, other things where the core has to store energy. And it stores energy in the gap because energy is proportional or 1/2 BH, which means areas with high B, which are in the core path, and high H, which is outside of the core, store the most energy. So that's the gap here. But you also see that the gap or the high H field extends away from the gap. So that's your fringing field. And if you happen to put copper in there, you're going to be inducing currents in those coppers pieces. So here's your current distribution here. And those pink areas are bad. So here's 3 different designs. This is a 45-watt flyback example. In our windings here with a single gap, we get a winding loss of 337 milliwatts. And this is simulated in FEM, the free 2D FEA program. We can actually split the gap into 3 different segments. So this is a distributed gap. And some manufacturers are actually producing these and selling them for this purpose. And because each gap is smaller, the field extends less. And the loss is almost half, maybe about 60% of what we had originally. So you might think, okay, well, maybe 3 gaps is better than 1 gap. What about an infinite number of gaps? So what happens if we use, say, a powdered iron or some hypothetical powdered material with a low mu such that the total magnetizing inductance is the same as what we had in this case, or in both of these cases? And well, you can simulate that, and you get something like this, and this looks very different. And what happens is we have a mu of 8 because we have no gap, and that low mu, so these are like 1,000 or 2,000. A mu of 8 means it doesn't really hold on to the flux anymore. It doesn't constrain the flux within the core. So a bunch of field, a bunch of flux just goes through the whole core. If you have good eyes, it actually extends away from the core too. So you get a lot more EMI with this. And you actually have higher losses than you start with. So this is not a good case. So we see that the single gap has a large fringing field. Distributed gap is pretty good at reducing it. But ungapped materials like powdered iron are not effective in this particular shape at doing what you want them to do. So one thing you do notice is, or in the market, powdered irons almost always come in toroids. And the toroid shape, the geometry, and the way you wind it means the winding structure itself is very good at keeping the flux contained. Whereas this structure, if you take away the core, basically looks like a solenoid and broadcasting your field everywhere. So there's some logic behind that. All right, we can take a look at another example of fringe field losses. This is an ETA-Designer. So ETA-Designer will calculate the fringe field and basically color your windings, put a color code on them based on how much AC to DC, or AC loss there is compared with the DC loss. If you do what you do as like a undergrad student in power electronics and fill your entire window with copper, you actually get the worst case loss here. It's about half a watt because your copper is so large and so close to the gap. If you put it on a bobbin, which you have to do for manufacturing, your windings are smaller, your DC loss is going to be higher, but because your losses or your windings are far from the gap, you actually save a lot of power. It's maybe 200 milliwatts. It goes down a fair amount. If you take, by the same spirit, if you say, okay, maybe I'll push them further away from the gap by adding some tape here, you can optimize it. This is just empirically optimized to be about 308 milliwatts. So that just shows you maybe optimizing DC loss isn't the whole thing. And there's actually a paper, again, Dr. Sullivan's group, showing how in 2 dimensions you can shape your winding in your window to minimize the total resistance, the total loss. And here again is the same 3 things simulated in FEM. The previous slide was ETA-Designer. So you can see that we match very well. There's slight differences due to the fact that ETA-Designer uses real waveforms. FEM just uses the first harmonic current waveforms. So they're going to be a little bit different, but give the same relative performance. All right, this is just a quick slide. Actually, for the instance of time, or for the interest in time, I'm going to skip this, but it'll be available online. Show you how these things are calculated, and there's a few good references here. Okay, capacitances. There's 2 major capacitances to consider, or 2 major types of capacitances. There's intra-winding capacitance, and these are shown in blue here, and they're between turns of the same winding. So they add a distributed capacitor in parallel with each winding. And this one, for example, connects the switch node to a DC or input node, and that will cause additional switching loss that maybe you didn't predict. And also add some resonant modes that are also detrimental and difficult to predict. So inter-winding capacitance is the capacitance between turns of separate windings. So here we have capacitance between the input switch node and the output. And that's going to inject common mode noise into the output. And that's something that's very difficult to get rid of, and it's going to cause you problems and signal integrity. And also in the EMC lab when you're trying to push out your product to manufacture, the last time you want to see problems. So that's something to consider. There's ways of reducing this. So single layer windings means that adjacent turns have very similar voltages and thus won't have a lot of effective capacitance once you extract the capacitance from the model. If you have to do 2 layers just to get the number of turns, you can, instead of winding like this, which is the worst case, You can do something like this, which means the adjacent turns in the different layers are actually pretty close in voltage, and they won't contribute much in capacitance. And that'll actually push your resonant frequency, your transformer higher, and your parasitic losses will get much lower. In terms of inter-winding capacitance, you can either move the windings farther apart, which is a very brute force way of doing it, or adding a shielding layer. So this is a single layer foil, and you can represent it as an auxiliary winding. You want to ground it, and you want to ground it to a quiet node on the same side that your noise is being injected from. So our noise source is the switch node on the primary side, so we tie our foil to a quiet DC node, and a flyback, it's the positive rail. And that'll keep the switching noise on the primary side. Okay, so now let's talk about scaling. Everyone wants to make inductors smaller. That meets the number 2 goal, and indirectly the number 1 goal. If you make an inductor smaller, it's probably cheaper. So we'll start by looking at a buck converter. It's a very simple thing, but we have some ripple in the current of the inductor and a DC bias. So there's 2 main operating regimes here. There's a saturation limited area where basically you're either operating at small ripple or at small frequency, or perhaps both, some area in here. And that basically means, okay, we need to keep the peak current here beneath the saturation in the inductor, but our core loss isn't dominant, it's not too much of a headache. It also means our gap is likely small, and our fringing fields or our AC effects are probably negligible. On the other hand, if you have high ripple and high frequency, now we're approaching the area where, okay, your core loss is going to be dominant, and you're probably not going to be operating anywhere close to saturation. And this means you're probably going to have a larger gap, and that larger ripple probably means you're going to be needing to consider the AC effects, the skin depth, the proximity, and your fringe field losses. So let's take this a step further, and we want to create a representation of the power capability, the VA product of a magnetics designer, transformer, inductor in general. So we have an equation here. It's a little difficult, or it's a little long here, but I'm going to work through it. So we have our VA product, or our power handling capability, which again is a product between the applied voltage to the magnetic, the transformer, and the inductor, times the winding current through it. So that's a rough proxy for the power handling capability. So if you work this out, and this is all from the paper here, you can obtain from Dr. Sullivan's website. So the voltage is related to the maximum flux in the core, given by the maximum flux density times the core area. And then we're looking at the current in the winding window, which is a similar expression here. The turns ratio cancels out, so it's very generalized. It's not based on specific voltage values or current values or things like that. And we get something like this, where it's proportional to frequency and proportional to the core window times the winding window. And that's actually really interesting. That means that for the low frequency operation, or your saturation limited, we actually see that power is proportional to a linear dimension, called the linear dimension alpha, to the power of 4. So that means if you double your magnetic size, the volume goes up by a factor of 8, but your power capability goes up by 16. So that means the bigger your power system, the more effective your magnetic is. And that's at low frequencies. And also, power is proportional to frequency here. If you double your frequency, you can handle twice as much power in your magnetic. So that's your low frequency idealized case. Let's look at a few more cases. So we just talked about the top case. So power density increases linearly with size. Same with increases linear with frequency too. But not everybody's saturation limited. Actually, that's a rare case for inductors or for very low frequency designs. When you get core loss limited, now you can't scale the bigger your core is, you have to scale down your flux density because you can't get the heat out. The heat dissipation is proportional to the area. The amount of heat generated is proportional to the volume. They don't scale equally. So we get much closer to a linear or constant scaling factor. The variance there has to do with your Steinmetz parameter beta, which is between 2 and 3 gives you this variation here. Now with frequency, you don't get a factor of 10 every decade. You get something that's like F times some peak flux density function of F. And if you remember, that actually is the same material performance factor we saw earlier here, and we saw the diminishing returns as you go higher in frequency. And finally, at high frequencies, your windings aren't nearly as effective anymore. And when you scale up in volume, you don't get to use the whole winding window because of the skin depth and all those AC effects. So then you see these other scaling factors. So now with size, your power density goes down and not up. And your frequency scaling becomes yet smaller again. So anyway, that's taking a look at scaling. Now let's take a look at some of the case studies. So here's a flyback converter. And we're going to be looking at the magnetics of this, but we're going to look at it in ETA-Designer. I'm just going to walk through a quick design. So basically, we type in our specs. We're going to simulate a DC to DC converter. I know they're AC to DC, but the bridge rectifier stage is boring. We all know how that works. Essentially, the flyback is where it's at. So we'll put our input voltage from 90 to 350 DC, output voltage of 19, and up to 3.5 amps. So that's a 65 watt laptop adapter. If you're not familiar with the specs, everyone has one. So we have create a converter here. So we're actually going to modify it to be a valley switched mode, which I won't get into the details, but anyway, we can specify the control here. We can put constraints on the edge. So for example, here we limited the period or the switching frequency between 50 kilohertz and 140 kilohertz. And we actually switch when you get a valley in the voltage waveform, which improves your efficiency. But anyway, if you choose a semiconductor device, it lists all the devices here, pulls out the prices if the part number is correct, and it substitutes the device into the circuit, evaluates loss, so you can pick which part has the best performance. Here's the magnetics design. So you can pick your core geometry and material up here. You can come down here and choose your air gap, magnetizing, inductance, or primary side turns count. And these 3 parameters are all linked. So you can choose 2, and ETA-Designer will calculate the 3rd based on what your constraints are. So for a flyback, for example, you want a controlled magnetizing inductance, so you select that and calculate the air gap. For a half-bridge transformer, for example, you would have no gap. You put 0 here and it would calculate the other 2 for you. Or sorry, you'd specify the 0 as the air gap in the turns count and it would calculate the magnetizing inductance. The next step is to add your other windings. Here's an auxiliary winding to power the controller. And then you can edit the windings, so you can choose solid or LITs or foil or PCB winding, your gauge. You can automatically size it to fit the winding or to fit the window, so you don't have to choose it automatically. Then you can choose the insulation thickness you have. And here we choose 6 parallel strands. And then we can arrange our windings here by just dragging and dropping them, so you can make the layout look exactly like how you want it to. You can drag them around to minimize capacitance or minimize your leakage inductance, and actually calculates that for you there. And minimize your losses, so you can see your losses here. And on the next slide, on the next page, you can actually see a breakdown of the losses, your DC loss, your AC loss, your core loss for each of the windings. So you can understand where all your losses come from, maybe make some choices of positioning or wire choice. Here's a nice board. It's made by this company who's very graciously gave us the space here. But since most papers, for example, make hardware and show the results from that. Since we're making software, we take off-the-shelf hardware because everybody can use that to validate. Plus, it's a lot cheaper than building your own custom power supply. So anyway, we took this 65 watt flyback adapter here, and there's a transformer there. So we pulled it apart, and that's what this model comes from. It's the model that represents this transformer as closely as possible. I'm not exactly sure what core material they use, but in terms of the geometry and the wire gauge, it's all right. So now let's see how does the efficiency prediction from DeDesigner compare with the measured results? And more importantly, how important is it to consider these AC losses? So I ran the simulation twice, well, 4 times. This is what you get from DeDesigner. You get it, and we swept it over both the low line and high line to essentially reflect what we have from the data sheet. The numbers are a little bit different. This is from DC input. This is AC input, so you have a square root of 2 difference. So the results are here. This dark curve is the measured results from the data sheet. And the lower curves are here are the simulation, including AC losses, basically by the default values that the DeDesigner gives you. You can see that it's pretty darn accurate. It's within 5 to 10% loss calculation, which is as good as you're going to do with the datasheet models in standard calculations. If you don't consider AC losses, you're about 4% higher, which is about a 30% difference in loss. And that's if you do your calculation without loss or AC loss if you do your calculation without considering AC losses, you can get a nasty surprise when you get your board back and realize that you didn't consider it, your wire's too big or too close or arranged poorly, and your efficiency isn't anywhere close to what you expect it to be or what the specification says it has to be, so you have to do an entire redesign. So that's a flyback converter. Now I'm going to quickly talk about an LLC converter. So this is a resonant converter. Target at much higher power. So we're going to be looking at a 500 watt converter here. Maybe I'm targeting maybe 98% efficiency. So the way an LLC works is you have a resonant capacitor here with a resonant inductor, but your magnetizing inductance comes into play and is used to soft switch these transistors as well as the secondary side to achieve 0 voltage switching or very high efficiency. So your waveforms, so here's some design equations. I'm not going to go through them in the interest of time. But it's a fairly complex converter to design because of the 2 resonances involved. But it's becoming more popular now because it can be made very small and efficient. So here are our waveforms. We have a sinusoidal resonant current, more or less in red here. Half sinusoids in the secondary side rectifier. And most importantly, our primary side switch node here in blue has these nice soft transitions. They're linear here because DeDesigner uses a linear model. But you see we get ZVS on the primary side switching and ZCS, or zero current switching, on the secondary side, which means there's very little switching loss. But this all translates to requirements on the transformer. So this is a cross-section of a planar transformer. As I said, they have poor DC loss, but their AC loss is very good because these windings are very thin and they're interleaved, so you get hardly any proximity effect. But what we're studying here is the effective magnetizing inductance. So magnetizing inductance, again, places a requirement on the gap of the transformer. We were comparing 2. What's the difference here? The left one is using a silicon transistor on the primary side. The right one is using a GaN, or gallium nitride. This is a brand new technology and has much lower capacitances than silicon. So even though these transistors have the same resistance, the silicon version needs a magnetizing inductance of 50 microhenry to achieve soft switching. The GaN needs 200 microhenry. So that's a lot less circulating current. And most importantly, it's a smaller gap. That means you have much less field emanating from that gap than you would over here. And that means we have way less loss. So we have about 2.5 watts less loss in the GaN version than in the silicon version. And in a 500 watt converter, that's 0.5%. When you're shooting for 98%, it's a lot, but every 0.5% is a huge difference. It's a difference between 97.5 and 98 or 98. So that's a big difference there. So anyway, this basically highlights the fact that when you're designing power converters, not only do you have to consider each component on its own, you have to consider the effect each component has on the design or selection of every other component in the system to truly optimize it. And anyway, with that, I'd like to conclude my talk. So basically, we've seen that magnetics design is very complex with many trade-offs, both within the magnetic design itself and in the whole system. And custom designs, because of this, custom designs are needed for almost every power supply. Now, magnetics design comes down to understanding the losses and the trade-offs in the context of that specific power converter. So we've seen the Flyback and LLC have different constraints and different loss or dominant losses. So the things that are easy to calculate are DC losses. We've seen that, but if we just do DC loss and maybe calculate core loss, we've basically swept half the number of losses, or half the losses under the rug, and you'll probably end up getting bitten by them. So other things to consider that are very difficult are non-sinusoidal waveforms for core loss, as well as the AC effects like skin depth, proximity, and fringe field losses that need a software tool to really calculate. Finally, we've seen that understanding the trends in magnetics designs, how they scale, what the loss trade-offs are, can really help drive converter design decisions. So maybe you don't want to switch at a megahertz like you thought you would because the magnetics, your AC losses will be too bad. Maybe 500 kilohertz would work even better. And software like ETA-Designer can actually really help you understand all these trade-offs in the design so you can quickly and easily iterate to arrive at an optimized solution. So thanks for your attention, and I'll spend a quick minute talking about ETA-Designer. This is a software that my company produces. You can actually go to etadesigner.com and download a trial version for Mac and PC. And watch instructional videos like how to create a quasi-resonant converter, how to create different types of controllers, and adding your own device models and these custom magnetics. There's also a demo or a computer in the back running it, so you can take a look at it right now. I can, if there's time after this, I can give a quick or show you guys how to use it and answer any questions. So that's it. Thanks.
All right, thank you very much, Mike. So we'll leave it up to you. I'd say, we have approximately 15 minutes before we really got to wrap it and quickly clean up and get out. So I'll leave it up to you how much you want to do in terms of taking Q&A versus giving people a chance to see the demo over there if they didn't get a chance to see it beforehand.
Let's start with some questions.
A number of the magnetic losses are somewhat dependent on temperature. So how do you handle knowing what temperature your component's going to be? Certainly your eddy current losses are highly dependent on that, but even hysteresis loss is somewhat dependent on temperature.
Yeah, so certainly many of the core material-related losses are related to temperature. I haven't yet incorporated that into the model. That's definitely on the to-do list. The challenges were limited by the information the data sheet or the manufacturer provides. So until the manufacturers provide this temperature-related data in a more or less standardized way, at least standardized enough that a computer can interpret it, it's very difficult to incorporate that. There's definitely a little bit of data that you can use to extrapolate, and that's something we'll be doing in the future. And we can probably wrap some error bounds around that, but it's definitely something that needs to be done. Let's see.
A lot of the loss figures are done with AC sine waves.
Yeah.
And sometimes they're given in peak flux density or RMS. So, but a lot of the waveforms you're dealing with are not sine waves. So do you handle that by doing sort of incremental, I think you had one
Yeah,
plot.
I had a quick slide showing there's actually a number of mechanisms out there, or methods of various degrees of accuracy about how to extend these Steinmetz
There it
parameters.
was. Yeah.
Right there. Extend the Steinmetz parameters, which are taken on sinusoidal waveforms, into non-sinusoidal waveforms. So this, for example, breaks up your this is actually a rectified sine wave as an example. So this could be any switching waveform. You break it up into piecewise linear bits, and you can get that to any degree of accuracy you want. So then that means that the instantaneous power, or this IGSE method, which is a good compromise between being easy to use and quite accurate, takes each chunk here and so that the instantaneous power dissipation during that set of time or that chunk of time is a function of both the overall amplitude here of the waveform times the dB/dt, or the derivative of the flux density at that over that segment.
Do you incorporate this and use it quite a bit?
Yeah, so that's what we do to look at any arbitrary waveform.
I wanted to ask about proximity losses and the modeling. So do you do that only between layers, or are you doing it within the layer itself?
It's done on a two-dimensional basis, so within the layer. So the Dowell's equation is only a 1D approximation, which is not really sufficient for many layouts. So if you put your windings side by side, or you have more than two windings, you're kind of out of luck, or if your windings aren't infinitely tall. So what we do is, let's see, there is a quick slide in a little bit. Basically what we run is a 2D FEA in the program, a field analysis, and then we use, we find the field at each winding location and use specific equations based on the wire geometry to anticipate what the loss is going to be for that field. And that's known as the square field derivative approach. And there's a few references here talking about how that's done. So that can be done very quickly, and it's quite accurate. Sufficiently accurate, I mean, in terms of magnetics losses, you're going to be looking at the plus or minus 20% is going to be all as good as you're going to get, and as good as you're really going to need. But that gets you there.
Anyone else? We're just anxious to go and demo it in the back. Okay, well, let's thank Mike one more time. Thank you. And as I'm sure comes as a major surprise to him, we, yourself not excluded, would like to honor you with this certificate of appreciation. Well, thank you. Thank you.